Hello everyone, my name is AZRI Azhar. My name is AZRI Azhar and my matrix number is 23002072. So today's topic is reactive mixtures and combustion. We will focus on how combustion processes affect thermal system performance, efficiency, and energy utilization. So it will be more direct to engineering applications in thermal systems. But in the topic of reactive mixtures and combustion. So why do we need to study the combustion? Combustion occurs at many engineering sites such as power plants, internal combustion engines, aircraft propulsion, and industrial furnaces. So all of these use the combustion. Because what? Because the combustion is very important for them. For they to do their work. To do their work. Everyone can do their work perfectly, but so we need to measure their efficiency. So our goal here is to convert chemical energy into useful work efficiently. Combustion is one of the most important energy conversion processes in engineering because it is used in worldwide such as engines, power plants, turbines, and even industrial furnaces. So like I said, the main objective here is to convert chemical energy stored in fuels into useful work. So we need to know how efficient is it. Every combustion process requires two components. It is fuel and oxidizer. In most engineering applications, air supplies the oxygen needed for combustion. So we don't need to think about the oxygen because the air already provide us with oxygen. So the fuel examples are methane, octane, coal, and hydrogen. But the air comes with 21% of oxygen and 79% of nitrogen. For the fuel examples, methane is, as you all know, CH4. Octane is CH18. And coal is used worldwide, such as in the traditional trade, we use coal for the combustion to make it move to another direction. So the work there is efficient, but we no longer use the coal for the trade. So what is complete versus incomplete combustion? Combustion can be complete or incomplete. Complete combustion produces carbon dioxide and water while maximizing energy output. Incomplete combustion generates pollutants such as carbon monoxide and soot. So we have here C, like before, CH4 plus 2O2 plus O2, we will get carbon dioxide and water. But how many of it we need? So as you see, both here is enough because the carbon is enough. So we need to change the oxygen and water. But we need to calculate over on the left side we have 4, so but on the right side we have 2, so we need to add 2 on the water. 2 H2O plus CO2 plus CH4, and then the O1 on the right side we have 2O, right, 2 oxygen and 2, so on the right side we have 4 oxygen. So to make it 4, we need to add 2 O2, because 2 by 2 are 4. For the incomplete combustion, the carbon monoxide formation, or we call it pollutants, and soot are made. So incomplete combustion is equals to lower efficiency. What is the air requirement in combustion? So the air requirement, theoretical air represents the minimum air needed for complete combustion. Engineers usually supply excess air to guarantee complete burning, but excessive air can reduce efficiency. So we have here, theoretical air is equals to minimum air required. And excess air improves combustion. Like too much excess air, but if it is too much, it will reduce the efficiency. So we need to put it just nice. It is just nice, like 150%. So we will have 50% excess air. It is not too much, and the excess air is there. And then next we have energy release during combustion. The energy released during combustion is quantified using heating values. HHV includes the latent heat recovered from water condensation, while LHV assumes water remains as vapor. So we have water condensation here. Water condensation. Water remains vapor. So like to be here, gasoline lower heating value is 44 megajoule per kilogram. Moving on, we have adiabatic flame temperature. Adiabatic flame temperature represents the highest temperature achievable during combustion. It is a critical parameter because it influences efficiency, emissions, and equipment design. So, maximum combustion temperature achieved if no heat loss and complete combustion. No heat loss and complete combustion. Factors affecting flame temperature is fuel type, air-fuel ratio, and excess air. What is the importance of it? It is important. Importance. Material selection. Material selection for engine performance. And thermal efficiency. Next, we have exergy versus energy quality. Energy tells us how much energy exists, while exergy tells us how useful that energy is. What that means, during combustion, some exergy is destroyed due to irreversibilities. So, the energy is conserved. But exergy measures usefulness for work, measures efficiency of energy. Fuel has high exergy. Exhaust gases have lower exergy because it already in a combustion, so it will have low exergy. We already use the exergy, so it is logic that it is lower exergy. Exergetic efficiency. Exergetic efficiency evaluates how effectively fuel exergy is converted into useful work. It is often a better indicator of system performance than traditional energy efficiency. So efficiency is useful output or fuel exergy input. So we need to calculate their efficiency. For example, we have fuel exergy is 100%. So the useful work is 40%. But the useful work is similar to efficiency, so its efficiency is 40%. Engineering application. Where will we need to use this all? We need to use this all. For example, we have steam boilers, gas turbines, automobiles such as car, lorry, and motorcycle, aircraft engine, and industrial furnaces like on the factory or something. So in the end of it, combustion converts chemical energy into thermal energy. Air-fuel ratio influences performance. Flame temperature affects efficiency, and AZRI measures energy quality. In conclusion, combustion analysis involves much more than balancing chemical equation. Understanding heating values, flame temperature, and AZRI allows engineers to design more efficient and sustainable energy systems. That's all from me. Thank you.